All right, this is a fifth problem dealing with cylindrical and spherical coordinates. Our problem is evaluate the triple integral over region W of x e to the z squared, x times e to the z squared, dv, where a region W is given by x squared plus y squared plus z squared less than or equal to 17, and 1 less than or equal to z less than or equal to 3. Okay, so the first thing I'm going to do is try and visualize the region, see what's going on here. So the first bit, this x squared plus y squared plus z squared less than or equal to 17, that's a sphere centered at the origin. Radius is square root of 17. So that's a little bit weird, but let's go and try and draw this out. We'll do a z. I like to sort of draw a cross-section, maybe in the zx, or you could call it zr for the r in cylindrical being a radius, or maybe even zy. So we have some kind of circle. That's radius square root 17. And then these other bounds, z goes between 1 and 3. These are planes. So here's z equals 1. Let me do another one in red here. Z equals 3. And so we're looking at this region between those, and that's rotated around here. So it's going to be some kind of almost disc-shaped thing here with a little bit of a curved side. So in Mathematica, we can get a sense of what this looks like more precisely. So here's our three-dimensional image here. So this bottom is z equals 1, top is z equals 3, and then we have a sphere where we sort of just cut that down here. So this is really the shape we get. You could continue this on to a sphere, up, sort of finish the dome, and then go below. We get this sort of, I don't know, bowl-looking thing, maybe, here. Okay, so that's the region we're integrating over. Now, this region you could integrate in spherical or cylindrical coordinates. We'll do both of those. They each are going to end up using two triple integrals. But this is an example of a problem where you can do this without sort of evaluating an integral at all. And the trick here is if you notice you have this x here. So the function you're integrating is an x. Well, x times e to the z squared. So that's odd in terms of x. So what that means is that if your region is symmetric about the plane x equals 0, that's the yz plane, then your integral is going to be 0. And that's exactly what's going to happen. So when we look down here, here's this green plane is the plane x equals 0, or the yz plane, and we get sort of the same sort of image with positive x's on the right and negative x's on the left. So what we can think about is this is odd in x, and so if we integrate with respect to x first, that integral will be 0, whatever we have for bounds, and the whole integral will end up to be 0. So right away, what I get, sort of shortcut, I can get triple integral over w, x e to the z squared dv equals 0, and this is really by symmetry of w sort of about the maybe yz plane here, or we could say x equals 0. Here, symmetry of w next yz plane, and x e to the z squared is odd, really, if I just sort of view that in the x variable. So in some sense, we get the 0 that way. Okay, so quick and easy, that's how you probably really ought to do this question. But we can kind of go through the exercise for the sake of just to set up the cylindrical coordinates and spherical coordinates for this kind of shape. Imagine you didn't have an x there, you had something else. So I want to use the technique anyway. So let's do, how about cylindrical first? So I'm going to do cylindrical coordinates. And so my integral, I'm going to get a triple integral of x e to the z squared. Except I should switch that to cylindrical. So the x, that would be r cosine theta. E, z is just z. And then I pick up an r for my Jacobian with cylindrical. Now, I need to set up my bounds, or my order of integration. Now, one thing I'm going to do, I'm going to do d theta first. So theta, this is going to rotate around perfectly. There are no bounds in terms of theta for either r or z. So theta is going to go 0 to 2 pi here. And then what we want to do is we want to set up bounds for dz and dr. I'm going to do dz first and then dr. Now, one issue here when I think about the r is if I'm sort of out, let's just sort of draw, there's some line down here. Let me draw just a, draw a straight line here. So if I'm to the left of this line with my r, z starts at 1 and goes to 3. But if I'm to the right of this line, z starts at 1 and goes to this sphere equation. So that tells me I'm actually going to need 2 triple integrals to set this up. So I'm going to get 1 triple integral plus another triple integral. Everything's the same so far. Cosine theta e to the z squared r d theta dz dr. Let's look at the pictures of these two regions here, just so we get a sense three-dimensionally of the two parts here. So when we go down, this is actually the region here where you have z going 1 to 3, where that r went out to some point. So that was, on my graph, that was sort of this r to the left of this orange line. To the right of the orange line, the sort of accurate picture here, Mathematica looks like this here. So we get sort of a donut-looking thing, I guess, here. You've got this on the bottom, this is z equals 1, but on the top I'm going to go to this sort of curved surface here. And if I put those two together, here's sort of an image with those two together, you can see sort of the first bit in the red, the second bit in kind of the blue there. And so you can see how those sort of nest here together. And basically we're taking a cross section, whoops, like this, where here we go r equals 0 to some point, and then from that point out to sort of the final r. So those are our ranges. Okay, so let's go set up our integral bounds. That in mind. So z, the first one, let's do this at the left one. Z went from 1 to 3. On the second one, z starts at 1, but it goes to the sphere. It's sort of up to the sphere. Our sphere equation was, let me do this in another color, was x squared plus y squared plus z squared, well, equals 17 on the sphere. Less than equals 17 would be the ball here. X squared plus y squared is r squared in cylindrical. And so z squared is 17 minus r squared. So z would be plus or minus the square root of 17 minus r squared, but we know we're having z from 1 to 3, so z is the positive square root. So this upper bound is 17, square root 17 minus r squared. Okay, and now the r bounds, well, so what we need to do is the first integral, again, is going to get sort of the r bounds of this red circle, if we rotate this up, and the second integral is going to get sort of this blue kind of ring on the outside. So the red circle, well, that's, when we think about it in our drawing, that's sort of right here. So that's z equals 3, where that intersects the sphere. So what we get is our sphere equation is r squared plus z squared equals 17. But we know z is 3 when we intersect that sort of plane. And so we get r squared equals 17 minus 9. That's 8. So r is square root of 8, plus or minus, but we know it's a positive r. So what we're going to do is this sort of first one, we're going from 1 to 3. We can start r at 0, and we end up at square root of 8. Now, the second integral starts at that square root of 8, and then it goes out, so it's sort of the same square root of 8, and it goes out to this outer ridge here. Now, that outer ridge is the sphere. Let's see if we can rotate this down. It's not really going here. Oops, there we go. Rotate this down. So that outer ridge is the sphere when z equals 1 there. So what we can do is sort of the same kind of trick here. We can plug in r squared plus 1 squared equals 17. So r equals 17 minus 1. R squared equals 17 minus 1. R squared equals 16. That gives me an r is 4. So I go from square root of 8 out to 4. And there you have sort of set up in cylindrical coordinates here to be able to evaluate this integral. So let's go through and actually do the evaluation now. This is going to go really nicely. I'll say right away, I look at this and I'm worried about this e to the z squared. So I don't know how to integrate e to the z squared. In this first integral in particular, there's bounds. I mean, we're integrating over a cylinder, effectively, that red cylinder from the Mathematica drawing here. It means all my bounds are constants. There's no variables, so I'm not going to get a z to pop up in some integration. So I'm kind of worried about that. Something nice is going to happen, though. Second one, still, there's no z's in my bounds. I have an r, but no z's. So I'm worried about integrating e to the z squared. So this is where I'm going to rely on doing theta first. So I'm going to get my first integral. This is 0 to square root of 8. Integral 1 to 3. Okay, I get the stuff without theta is r times r. That's r squared I have an e to the z squared. And then cosine theta integrates to sine theta. And I do that, evaluate from theta equals 0 to theta equals 2 pi. And then we have a dz dr. The second integral, I'm going to add this through. We get a square root of 8 to 4, 1 to square root 17 minus r squared. We get the same r squared e to the z squared. I'm going to clear some space here. And I get times cosine, no, not times cosine. Well, it would be cosine theta, but I want to integrate that, and I get sine theta, where I go from theta equals 0 to theta equals 2 pi. And again, it's a dz dr integral. Okay, so now when we evaluate this, well, sine of 2 pi is 0, and sine of 0 is 0. So you get 0 to square root of 8, and I go 1 to 3, r squared e to the z squared, 0 minus 0, dz dr. Same thing with the second integral, square root of 8 to 4, 1 to square root 17 minus r squared. I get r squared e to the z squared. I get sine of 2 pi is 0, minus sine of 0 is 0. dz dr. So now our integrand becomes 0. The function we're integrating becomes 0 on both of these. So this whole thing ends up to be 0 plus 0. That gives me a 0. Okay, so cylindrical coordinates, this works out. Not that bad. I mean, it's a little bit tricky. You have to split into two integrals, do some work. None of the integration is hard the way we did this. Note, if you tried to put that d theta on the outside and integrate with dz first, you're going to run into trouble, because you're going to have to integrate e to the z squared, which does not have a sort of nice antiderivative. So the theta on the inside is really the way to go. A lot of times you can do that with the trig function. Sometimes they'll give you a 0 and it'll save you work. And that's even if you didn't pick up on the symmetry of the problem right away. But symmetry is probably the way to go, really. Okay, let's do this in spherical as well. So let's do this in spherical. So what we're going to get here, let's maybe just go redraw our picture here. So we have a sphere of radius square root 17. This is the sort of x, z. And then I chop this with planes z equals 3. And then there's another one at z equals 1. So in spherical, what we're going to do is we're going to think about, okay, start out sort of for rho. So let's set up the spherical. So let's just do this as spherical. We have an x. So it was the function we're getting is x e to the z squared. So the x is rho. Well, it's going to be a cosine theta, but generally write this as rho sine phi cosine theta. E to the z, z is rho cosine phi squared. And then my Jacobian is rho squared sine phi. And I have to set up an order of integration. Again, I'm going to use the same trick with cylindrical. I'm going to do theta first, and I'm going to hope that that gives me an integral of 0, and I don't have to really worry about the others, but we can set up bounds anyway. Then I'm going to do d rho d phi. Whoops. D rho, and then d phi. Those are my bounds. What I'm going to get then, okay, theta, I rotate all the way around. Theta goes 0 to 2 pi. Now you can look at this and see the only theta here is the cosine theta. So I'm going to integrate cosine theta from 0 to 2 pi. That's going to give me 0. So I look at this right and say, well, this is 0. Even have to split this up into two triple integrals. Each of them will be 0. Here, I don't really care what the bounds are. So you don't technically need to do this, but the point is, how do I set up the bounds for the shape? What if I had a more complicated thing? I didn't have that cosine theta. Okay, so that's theta. Now, phi and rho. Well, let's look at rho here. So rho is going to start at the origin. So let's just take a sort of ray out here. So here it's going to start at the origin. It's going to go, at this point, I sort of get into my surface. So that's at some point there. We had to find an equation for z equals 1. And then I go out, and I sort of leave the surface at z equals 3. So we're going to have to come up with equations in terms of, for rho and phi, for z equals 1 and z equals 3. But if I go and, let's say, let's do an orange shoot out. If I shoot out over here, I'm going to hit that z equals 1, but then I continue on the surface. I sort of end, or out of my solid, on the sphere. So I'm going to end up with two different triple integrals, and these are going to split on sort of this ray here. So I'm going to get sort of this wedge-shaped thing. I'll draw this here too. Sort of this wedge-shaped thing inside as one integral. And then I'm going to get sort of this part with this part rotated around for the other triple integral. So you got my ugly drawing to look at. Let's look at Mathematica as well. So that wedge-shaped thing, here's what that is. So this is the black rotated around. You're going to get this part here, and you can see rho goes through the bottom, that's at z equals 1, and it goes out to the top at z equals 3. Now the sort of blue shaded part here rotated around, so it kind of looks almost like a triangle, but this side is curved. What that's going to look like is this guy here. So we rotate this in, and you can see it's sort of, well, the rest where that red sort of plug would fit in here, kind of a thing. So it's that rotated around. And when you put them together, sometimes it helps to kind of see what's going on here. What we've got is this shape here. You can see the top z equals 3. So that's where the red, I start at z equals 1 in both. In the red, I end up at z equals 3. In the blue, sort of the ray from the origin goes out and hits on the sphere. Those are sort of the visuals of what's going on. So what we're going to do is set up a second triple integral. I'm going to get a 0 to 2 pi, rho sine phi cosine theta. We have e to the rho cos phi squared. And then I get my rho squared sine phi. And I'm going to do this d theta, d rho, d phi. So that's really sort of our two integrals here. But now we need to do bounds. Rho. Well, let's think about phi first. Maybe phi might be easier. So on this black region, phi is going to start at 0. Starts at 0. And it's going to go out to whatever this angle is here. So on that angle, let's see if we can figure out what that is. What you could do is draw a triangle. So let's see here. Try to do this in sort of a bright green. I have a triangle sort of right here. So that triangle, what I'm going to get, triangle like that, there's my phi. This top, well, I'm at z equals 3, so that leg is 3. And the hypotenuse, that's part of that sphere of radius square root of 17. So that's a square root of 17. And so what I'm going to get here is that top is inverse cosine of 3 over square root of 17. So kind of an ugly bound, but it's cosine inverse 3 over square root 17. So that's what we've got. The other bound, I'm going to start at that cosine inverse 3 over square root 17. And then I'm going to have to do a different triangle to find sort of the angle when z equals 1. So that triangle, let me do a darker green here. So I'm going to have one side here, one side out here, and my hypotenuse there. So that's going to be a triangle like this here. Here's really the phi that I care about. That should be something slightly less than pi over 2. This leg is going to be 1 because that plane is z equals 1. And again, the hypotenuse is square root 17. So we get a phi being another inverse cosine. So cosine inverse of 1 over square root 17. So there's our phi bounds. Now our rho bounds, so the first one up here, we're going from z equals 1 to z equals 3. So we've got to write those down. Z equals 1, that's rho cosine phi equals 1. And that tells me rho is 1 over cosine phi. So that was the starting rho bound for the first integral. You get a 1 over cosine phi. The ending bound is the same thing, but I put a 3 where this z is. So what I get here is I get a z equals 3, and then rho cosine phi equals 3. And so I get rho equals 3 over cosine phi. So my upper bound is 3 over cosine phi. Okay. The other one, I'm going to start at, on this sort of orange segment here, I hit the plane at z equals 1. That's still the 1 over cosine phi. And I go out till I hit the sphere. Well, the sphere is going to have radius square root of 17. So I pick up a square root of 17. So there really is my big triple integral. Well, two triple integrals I have to do. Looks kind of intimidating, but again, when we integrate with respect to theta, we get to cosine theta. That's going to give us 0. So let's just run through that quick here. Our first integral, go down here, was we have an integral from, let's see, I forget what it was. It was cosine, or 0 to cosine inverse 3 over square root of 17. The next bounds went from 1 over cosine phi to 3 over cosine phi. And then the thing I'm integrating, let's just simplify, it's going to be the same thing here. I get rho cubed. So maybe write this down. I get rho cubed. Sine phi times sine phi is sine squared phi. And then I get an e to the, it's going to be rho squared cosine squared phi. And then when I integrate cosine theta, there, what I'm going to get is a sine theta. I have to integrate that from theta equals 0 to theta equals 2 pi. And then I'm doing d rho, d phi. So that's the first integral. Note this part is going to give me a 0, so that whole thing, so this whole thing here, that whole thing goes to 0. And then we're going to add to it, and we'll write the plus down here. The second integral, the only thing that's different is these bounds, but that doesn't affect the fact that we got a 0 here. So we're going to go from, this was cosine inverse 1 over square root of 17. Whoops, this was 3 over square root 17. I missed the square root in the first one. Cosine inverse to, wait, no. Let's go through. This one starts at cosine inverse. Oh, I think I have the wrong bounds here. Now I look at it. So I started at z equals 1. No, phi starts at cosine inverse 3 over square root, cosine inverse 3 over square root of 17 to cosine inverse 1 over square root of 17. That's good. Everything's good there. So I'm going to start at, but I start at the bottom bound is the 3. So this should be a 3. And this is 1 over square root of 17. I just got to make sure I had that correct. Yep. Okay, next bounds I had a 1 over cosine phi. Then I went out to square root of 17 out to the sphere. And then I get this same rho cubed sine squared phi, e to the rho squared cosine squared phi. And then I get the sine theta, where theta goes from 0 to 2 pi, d rho d phi. And what I'm going to get is this whole second integral also goes to 0. So I'm going to get 0 plus 0. That's going to give me 0. Okay, so we did this problem 3 ways. One is we use symmetry. That's probably the way you want to do this. It's quick and easy. You don't have to really think about things. We also did this in cylindrical coordinates and spherical coordinates. Part of the point of that is just to work on those coordinate systems and get some practice in.